In this video, we're going to talk about some properties of logarithms now that you've watched the Khan Academy Introduction to Logs. Specifically, we're going to talk about how logs are expanded or how they are written as a single log, and we'll talk about what's called a change of base. You may want to just take a blank sheet of paper and fold it in half and use those two questions as separators for your notes. Let's start with base 10 logs. This is something that I don't think Sal from Khan Academy really specifically talked about enough for me to feel comfortable not talking about it some more. Logarithms with base 10 are called common logs because they're the ones that are used most often. So when you don't see a base written, so notice here you don't see a base, it's assumed to be a 10. Sort of like if we have an x and there's nothing sitting in front of it, it's assumed to be a 1. So if you see log 10,000, then you need to ask yourself, 10 to what power will give me 10,000? And the answer to that is 4. Another special notation that you see deals with natural logs. Logarithms with a base of e are called natural logarithms. Natural logarithms are denoted by using just an L and an N. So ln with an x is the same as log base e of x. So on the calculator, in order to get to your natural log and your common log, you'll need to access the buttons that you see being pointed to here. You actually have an LOG button and you have an LN button. So let's review the 3 properties that we've already talked about. The first has to deal with common logs. If you don't see a 10 there within the common log, that's the same as there being a 10 base. The next has to do with a base of e. So ln means the same as having a base of e. And then just your formal definition of a logarithm and how to write that as an exponential is going to be y equals log base a of x, means the same thing as a to the y equals x. So I want to focus on some of the properties that you see up on the top here, and then we'll go through the properties, the product quotient and power properties that you see down below. First one that I want to look at is that log base a of 1 is equal to 0. That was something that Sal talked about in his video. Anytime you see a log, no matter what that log base is, if there's a 1 there, the answer is going to be 0, because 0 is the only thing we can raise a number to in order to get 1 back again. So I might have log base 200 of 1, that's going to be 0. Log base 10,000 of 1, that's also going to be 0. Moving on to the next property that you see over here to the right, let's talk about when the base and what's sitting next to it match. If they match, then the answer has to be 1, because 1 is the only power that we can raise a number to get the number back. For example, if we have log base 2 of 2, the answer has to be 1, because 2 to the first power is what gives us 2 back again. I don't want you to focus too much on this property here, but I do want you to look at this property here. And this property says that if we have an exponent, the way we can get that exponent isolated is to take a log of both sides. And we'll be using that idea when we solve equations. Let's look now at the properties down below. The first property is the product property. And these properties should make a little sense based upon the rules of exponents. So the rules of exponents say if I have 2 cubed times 2 squared, you add the exponents together and get 2 to the 5th. Well, since logarithm and exponentials can be converted between one another, it would make sense then that if I have a logarithm, that's multiplication, I can break that apart into addition. And remember your properties of exponents with division. If I have 5 to the 3rd over 5 to the 2nd, sorry about that, 5 to the second. Then we're going to go ahead and subtract the exponents, and that gives us 5 to the first. So it doesn't surprise you then that if you've got a logarithm involving division, you can separate that into subtraction. And finally, this last property is the power property. And this property says if you've got an exponent up there, you can pull that exponent out in front of the log. So let's look at how you're going to be asked to apply this. If I have log 20 minus log of 5, and the directions say write as a single log, then I'm going to take the subtraction and turn it into division. So that's going to end up being log 4. Likewise, if I have addition, and this should just be 1/6 there, so ignore that, log 6 plus log 8, then I can combine it into one log with multiplication to become log 48. Sometimes your directions will say to write as a sum of logs that only have exponents of 1. So let's look at this here, and we're going to rewrite that as log 5 plus log x squared plus log y cubed. Now, if I'm not allowed to have any other exponents, then I'm going to use that power rule, and I'm going to bring those out in front. So we've got log 5 plus 2 log x plus 3 log y. Sometimes you need to change bases, and this will be especially necessary when we need to use the calculator. On the calculator, remember, the only buttons that you have is a log button, which is assuming a base of 10, and an ln button, which is assuming a base of e. So if we have log base a of x, we can evaluate that on the calculator simply by using the natural log of x, whatever is sitting in that x spot, divided by the natural log of a, whatever is that base. You could also use the LOG button, but this particular book in MyLabs Plus uses ln, so for consistency's sake, that's what I'm going to use. So here's an example. Find log base 3 of 7. So remember, that's saying 3 to what power is 7? Well, there's nothing I can do to figure that out. 3 to the first is 3. 3 to the second is 9. So it has to happen somewhere in between here in a decimal, but I'm not going to be able to do that without a calculator. So you'll use the change of base, and you'll evaluate it by taking the natural log of 7 and dividing it by the natural log of 3. And you'll do that directly on your calculator. Finally, I want to end with a visual of the exponential function and the logarithmic function. So notice that the exponential function, the domain was the set of all real numbers, and the range was the set of all positive numbers. Notice how that flips with the logarithmic function. The domain is the set of all positives, the range is the set of all reals. Whereas the exponential function has a horizontal asymptote with no vertical asymptote, the logarithmic function has a vertical asymptote with no horizontal asymptote. So this is a nice visual for you to compare the two functions to one another, and also to have a better understanding of how the domain and range compare between the two.